Today, we're going to talk about radar technologies.
Combination of a camera and a high-performance radar is really something that covers all of the cases.
In automotive industry, we call it sensor fusion.
Exactly. So the fusion is really what we care about in the end.
I love it. I love it. Let's discuss this. I like this kind of, this is something that I think our audience would love. The reason it's different from a LiDAR is number one, the wavelength. Now that you have decided to revolutionize radar technology, tell us a little bit about it. How is it going to revolutionize radar technology? Welcome back to another episode of Matrix Tech Talk. Today, we're going to talk about radar technologies. Some technology that's going to revolutionize radar technologies, radar industry. And for that, we have all the way from Tel Aviv, Noam Arkind from Arbe. Noam, welcome to Matrix Tech Talk.
Hello, thank you, and a pleasure to be here.
So Noam has a fantastic career. He's one of the co-founders of Arbe. He is working as the CTO of Arbe right now. He's got 10 years of R&D experience, and he holds a PhD in applied mathematics from the robotics lab at Weizmann Institute of Science in Israel. Noam, I'm really impressed. You know, I'm a computer scientist. I did my PhD, all my degrees, bachelor, master's, and PhDs in computer science. But when I really went deep in computer science, I felt that I should have studied mathematics. You know, I really envy mathematicians. So I'm really excited that we have a mathematician in the show. And yeah, without further ado, Noam, the first question I want to ask you is, how did it all begin? You co-founded a company, an exciting company, and we're going to talk about your company in a bit, but let me start with you. How did it all begin? Tell me about your passion. What inspired you to be an entrepreneur?
I think I always wanted to be an entrepreneur, but after I finished the PhD in the robotics lab, then I kind of gave me like a urge to try to advance this field, because my feeling from my studies and from meeting other people working in this field and seeing other works and other labs is this field is kind of stuck. So it's stuck in the academics, and the actual applications, industrialization of this field is not really moving like it should. And then I started thinking of why. What is really the barrier for the entire field? And I was also working during the PhD on another project of a small spacecraft that we built that was supposed to land on the moon. Eventually, it got to the moon, but didn't land. It crashed on the moon, but it got to the moon at least. And over there, I was working on real life control system, very complicated, a satellite that has to navigate in space. And from all of this, really what my impression was is that we should really divide this problem into three. So same way, it's like a classic separation that is done also by NASA. It's guidance, navigation, and control. So they have a GNC department. And so the control is really the low level actuation. Is how do you really move things? Guidance is really giving it guidance, telling him where to move and what to do. And navigation is really the perception, understanding what's going on around you and sensing the environment. So my impression from all of this is that we have a lot of great people and great algorithms for the guidance part, and really we can you give the problem to a very smart guy and he can solve the guidance issue most of the times. And we see this also in autonomous driving. So you see works from Waymo, Tesla, people, places like that, and they're doing an amazing job on really understanding the driving policies and how the car should drive. And there's the actuation part, the control, which is in autonomous driving, it's completely solved. We have great cars, great mechanics. And it's also the same in space industry, at least in my impression, that we can solve the guidance and the control is very difficult, but it's also, we know more or less what we can do and what we can't. But in the navigation part, in the perception, is really where we're kind of limited. So the sensors are that we have today are very expensive, very non-robust, very unreliable, and my impression was that we need really a breakthrough in this field, in this direction of perception and really understanding and sensors to really take this entire field of robotics to the next step. So let's say that tomorrow we will have amazing sensors that can sense everything reliably and in a low cost. Then I will think that the day after we're gonna have a lot of new robotics applications that are just currently stuck in that phase.
I can see the motivation that you see that there is a problem with the sensor technology compared to other parts of the robotics or autonomous system advancing, in your opinion, not as advanced as the others. You said that you always wanted to be an entrepreneur, right? And this idea came to you when you were doing your PhD and exploring the fields of robotics. Why do you want to be the entrepreneur in the first place? Let's go earlier in your childhood. Who inspired you? How did it all begin?
It's hard to pinpoint a specific moment. I guess that during my entire life, always admired the researchers and the smart people in every scenario. And that's what I wanted to be like. I wanted to be the one that creates new technology and
totally. I get it. I get it.
This progress, but I can't really say it was this moment or.
I know what you mean.
That made me want to go in that direction.
But I'm totally with you. I'm actually writing a book, and in one of the chapters, I'm talking about that entrepreneurs and scientists and technologists. They're the people, they solve all the problems in the world, not any other kind. Even in this global pandemic, I mean, there are several companies with their researchers and scientists coming up with the vaccine, right? It is entrepreneurs and the scientists who are coming up with solution, who moves the world forward. I am totally with you with that. So having said that, now that you have decided to revolutionize radar technology, tell us a little bit about it. How is it going to revolutionize radar technology?
If I'm relating to the introduction I said before, so we wanted to build like the dream sensor for autonomous platform. In my opinion, it has to be very reliable, very robust, and very cheap. The radar technology, at its basics, is that, right? At least when you're talking about relatively like millimeter wave frequencies and lower. When you go to higher frequencies, it's not as reliable and robust, but let's say in this area of millimeter wave frequencies, it's extremely reliable and very robust. So it works really in any condition. It's an active sensor. It's not a passive sensor. It's not greatly affected by environmental conditions. And we know how to build radars fairly cheap. So the real issue in the radar is the performance of the sensor, right? Mm-hmm. So we got this from day one. We got these features of reliable, robust, and cheap. And what we didn't have is the performance. This is what really is lacking in this radar industry. But we are good engineers and good scientists, so we wanted to solve this problem, and this is really what we try to do. We try to come up with new ideas, new architectures of how really we can increase the performance of the sensor without really increasing the cost and without really compromising on the other aspects of the system. So this is how it revolutionized the industry. So in the end, what you really want to do is have a full system with a high performance. So it complements I would say, the camera sensor in a way that a combination of a camera and a high performance radar is really something that covers the all of the cases.
In automotive industry, we call it sensor fusion. We need that.
Exactly. So the fusion is really what we care about in the end.
No, before we go to the fusion part, I'm going to come back to this. Sorry for the interruption. You put several very interesting points on the table. And for our audience, you talked about millimeter wave frequency radars, right? And they're extremely efficient. Can you explain to us a little bit first, why does the wavelength play a role in the efficiency or the performance of the radar, and how millimeter wave frequency is better than the other?
In automotive, we have really dictated frequencies that is allowed by the regulation, which is around 76 to 81 giga. It's about 3.8 millimeters wavelengths. The big advantage of going up in frequency is it's both the size and Doppler resolution and bandwidth availability.
Doppler.
And the size. So the higher you go in frequency, you can make the sensor smaller with more or less the same performance.
Smaller in size, you mean?
Smaller in size.
So higher frequency, smaller in size, and same performance. Got it. It's due to...
Up to a certain point.
Up to a certain point, and it's due to better Doppler effect.
You can get in the same time, in the same coherent times, a higher Doppler resolution. So you can get
higher Doppler resolution.
Doppler accuracy, yeah. Accuracy and performance. The main feature that is driving this is actually the size. There are actually two. The regulation, you don't want to occupy any bandwidth that is used for other purposes, but also you want to get the sensor smaller to integrate it easily into the car. So this is the main drivers for this frequency of around 80 giga.
Okay, around 80 gig.
Yeah, so when you go higher in frequency, things started to get a bit more complicated. So I would say the technology becomes a bit more expensive, less efficient. You can't get the same output power, same transmitted power. You can get the radar smaller, but at some point you're losing really the benefits of getting to higher frequencies.
So 80 gigahertz is the sweet spot that you have identified, right? So what would be the corresponding wavelength for the radar? With 80 gigahertz?
0.8 millimeter.
3.8 millimeter. All right, so that's the sweet spot you have identified. What is the size when you are actually using that frequency? How big are those radars that you're producing?
It really depends on the application. So you can find radars of all sizes. You can make, for example, antenna on package. On the package of the RFIC, you can print an antenna and make a radar in the size of, 1 centimeter by 1 centimeter or 1.5 by 1.5, something like this, which is extremely small. It's more a proximity sensor or something like that. But when you want to really get better angular resolution, better perception, you need to get the size a bit higher. This is really what you need for autonomous driving. You can't really use something that small. So we're talking about 10 by 10 centimeters.
10 centimeter by 10 centimeters, the sweet spot again for autonomous driving. Something like that. And what is the range of your radars?
Again, depends on the application. For autonomous driving, you need to detect cars and motorcycles in range up to 300 meters. Right, so the requirement is to detect a car at 300 meters, a motorcycle at 250 or 300 if you can, pedestrian at 100, 150 meters. This is more or less the ranges that we talk about.
As I understand, you're using the sweet spot you've identified. It's 80 gigahertz, it's 3.8 millimeter wavelength, and it has a very nice Doppler resolution. That's the sweet spot you've identified. It can be extremely small, 1 millimeter by 1 centimeter by 1 centimeter to, autonomous driving. You're saying 10 centimeters is a sweet spot, and you have different ranges. You also talked about, the angular coverage. What do you think of LiDAR? And what is your thought on that? I don't want to bring Elon Musk's radical standpoint on LiDAR. What's your standpoint on LiDAR?
it's something that we've been saying before Elon made his statement. We're saying something very similar.
I love it. I love it. Let's discuss this. I like this kind of, this is something that I think our audience would love. Why do you have such a radical standpoint from a technical point of view?
First, it's still not solving the problem of environmental conditions. So it's not really working well in rain and dusty and fog. So it still keeps you with a blind spot. So this is one. Second, is very expensive. Maybe they'll solve it, maybe not. Third, you get more information than you need, really. So imagine that you have a LiDAR and you look on a person, you can count how many fingers you have. But for autonomous driving, you don't need this amount of information. So really, you're getting tons of data. You don't have what to do with it. You have to filter it out mostly to extract what is really important for you. So you're making your system more complicated and more expensive, and there's no real need for that extra overhead. When, as I said, you really care about the fusion performance, right? So a radar, it's actually sensing 4 dimensions: range, Doppler, azimuth, and elevation. And
range, Doppler, and what was the third thing?
Azimuth and elevation, so direction to the target. Mm-hmm. So, and the range and Doppler perception is always good in radar. It's a technology that allows you to get really good range performance sensing, so the distance to the target, and really good Doppler sensing, which is the velocity, the radial velocity of the target. The issue was always the angular resolution. And why is it an issue? Because if you look on radars, automotive radars that are deployed today on a car, it's extremely low resolution. So imagine it has something like 10 pixels, angular pixels in the image. And now the camera, on the other hand, has great angular resolution, right? It's, I don't know, a 10 megapixels camera, have amazing resolution in azimuth and elevation. It is really the same dimension as the radar, the same azimuth and elevation, only with much higher performance. But it doesn't have at all range and Doppler. It doesn't have very good range performance and no Doppler performance. You're really interested in the overlapping dimensions, which is the azimuth and elevation. You use these overlapping dimensions to fuse the sensors, right? Because you need to know what's the azimuth, what's the direction of the target in the radar in order to fuse it with the target in the camera. So now the real question is on these overlapping dimensions, when is the resolution good enough to have effective fusion? Because once you fuse the radar target with the camera target, you enjoy both the range and Doppler performance of the radar, which is amazing, which it was always good, and you enjoy the angular performance, the DOA, the azimuth and elevation performance of the camera, which is always good. And if you get the fusion right, if you get these overlapping dimensions right in the radar, then you get a good sensor fusion. And once you get good sensor fusion, it doesn't really make sense to add a LiDAR. It doesn't give you any new information. Even if the LiDAR resolution is 10 times higher than the radar, you already got the resolution from the fusion. So there's really no point of adding this overhead to the cost and the complexity of the system. You just need to get the angular resolution right on the radar, which is challenging, but not impossible. This is what we are proving in Arbe.
How do you do it? So you have a LiDAR versus a radar, and you're saying if you do the angular resolution right in the radar, how is your approach different from traditional radar industry as you're revolutionizing it? Can you tell us a little bit about that to our audience?
The radar resolution is, there are all kinds of different ways to get it, but if I stick to the physical layer, right, to the physics, you get the resolution by adding more transmitter channels and more receiver channels. So you can think of it like pixels in the camera. We are building a radar system today with 48 transmit channels and 48 receive channels. Imagine like an image of 48 by 48. It's 2,300 pixels in an image. And on the other hand, the radars that exist today, they have 3 transmit channels and 4 receive channels. So they have 12 pixels. And the reason that they don't increase the number of channels is because it's considered very expensive. So our approach from the beginning is to find a way to reduce the cost per channel. So getting a high channel count, getting more and more resolution, reducing the cost per channel, so that in the end of the day, we get the high performance, but won't increase the cost of the overall system.
No, forgive my ignorance here. What would be the fundamental difference then between a LiDAR and multi-channel radar as you're talking about?
There's a lot of differences, right? First of all, the wavelengths. Radar works in a millimeter wave frequency, and the LiDAR works in a nanometer. The wavelengths is one key difference.
But for the angular resolution, the mechanism of doing the angular resolution right.
There are some radar types which are similar. Specifically, our radar is slightly different. In our radar, we do what is called digital beamforming, which really the benefit is that you get in one single snapshot the entire image. The LiDAR is scanning, so it shoots a beam in different directions and receive the energy from that specific direction, and then it builds up the entire scene one point at a time. And a radar based on digital beamforming is really transmitting energy in all directions simultaneously and receiving from all directions simultaneously. And then you get in one snapshot the information from the entire image and not just a specific point. There's 2 types of radar, I would say, a scanning radar and a staring radar. We are focusing on the staring radars. We think this is really what makes sense for autonomous driving. But other companies have tried to do scanning radars also. It's very problematic because you really have to make decisions already on the sensor level. Where are you looking at? Which areas of interest you have in the scene. So making this type of decision on the sensor level is extremely dangerous, not safe, and doesn't really make sense. You really want to get the entire image in every frame. So maybe I hope this answered more or less your question.
Yeah, I mean the question was when you were doing the angular resolution. So let me see if I understood your approach. Yeah, you're using multiple transmitters and receivers to get the angular resolution right. And the reason it's different from a LiDAR is number one, the wavelength. And what was this? I'm sorry. What was the second main difference again?
It's shooting energy in a specific direction and receive it in that direction. And the radar can do like a staring mode where it really captures the entire image in a single frame. So those are 2 differences in how it captures angular resolution. There's a lot of more technical differences.
No, I mean, I understand the technical differences. I mean, I was just thinking of the angular resolution.
The modulation scheme is different. So, the LiDAR shoots very short pulses, where the radar at least.
How does these relate to the angular resolution? Just for my audience to understand. Let's boil it down. Let's simplify it for the audience. How does a LiDAR compute the angular resolution, and how does your radar technology with the arrays of transmitters and receivers compute the angular resolution? And probably this will help us understanding the difference.
There's also the difference of mechanically, how do you really steer the energy? A LiDAR, well, I'm not a LiDAR expert, but the common method to steer the energy is by mirrors. So you have all kinds of MEMS structures, MEMS devices that really directs the light in different direction mechanically. And in radar, it's not like that. It's steered electronically. So you're using a phased array technique. So you're transmitting energy and receiving energies from multiple channels simultaneously. And you use different phase differences between the channels. And so you create a beam. that is directed in a specific direction. I'm not sure that all LiDARs work in this mechanical approach that's really steering with mirrors. I'm not a LiDAR expert, but all radars really work in a same kind of beamforming approach. It could be a digital beamforming, like we're doing, as I explained. It could be analog beamforming, where you actually transmit with different phases and not just doing it on the digital part.
Yeah, I mean, I'm with you. This is totally understandable what you've just explained. I remember when Google came up with their first, prototype. They had this thing on top which was moving. Yeah, I mean, these old days, the LiDAR was $200,000. The LiDAR price went down drastically, but people said, well, a nice research project. And this is nothing close to reality. But I think the LiDAR price went down a lot. I mean, of course, not as low as radars, probably. One very clear difference is this: you're not really mechanically moving the thing in a radar, but it's an array, and you're computing this based on the differences on the positioning.
Modern LiDARs don't use this rotating scheme. It's solid state LiDARs, but still they use beams with mirrors that really direct the beams. It's solid state, but still some mechanical parts.
Solid state with some mechanical parts. And here you're basing it on computation in your radar.
Yeah, you can say it's based on algorithms, signal processing algorithms.
Signal processing algorithm. Love it. Let's move on. I mean, you also talked about cost, which will come. We wanted to talk about sensor fusion, which we did already a little bit, but let's delve down in the sensor fusion domain. Try and simplify for the audience. So, like you said, you're receiving. Let's forget about LiDAR for now. So we'll pretend that LiDAR doesn't exist for today. So you have a sensor fusion, and you have the camera, which is sending you signals, and you have the radar, which is sending you signals. So now you have to fusion it, right? What kind of advantage in this fusion mechanism your radar will bring in? That's what we want to understand. And for that, if we can talk a little bit about how does this fusion happen with a normal, not that sophisticated radar as yours. And then we go to the scenario how your one will advance this fusion mechanism.
The basis to this advantage, I would say, is the fact that the two overlapping dimensions, which are the azimuth and elevation, we can provide much higher performance than any other radar that is available or in design today. So this really what it allows you is to do a fusion on a lower level than today. So if you look on the sensor fusion systems today, what they do is imagine that you have a camera and you detect objects in the camera using the camera and you track them, and then you have camera tracks. And you do the same thing with the radar. You detect objects with the radar and you track them, and then you have radar tracks. And then the fusion level, the fusion is done on this object tracking level. So you get the radar tracks and you get the camera tracks, and you're trying to understand which is which, and then you fuse both of them. The problem with this approach is really that each sensor by itself is actually limited. So the radar is limited. It has good Doppler perception. So Doppler is the radial velocity, but has really bad tangential velocity perception. So if an object is moving in a tangential direction, the radar ability to track it is becoming much more degraded than when it's coming in a radial direction. For example, there are other problems as well. And the camera, if it's dark, then it's really hard to track anything. So you really, in this approach, you suffer from the disadvantages of both sensors, and it's really hard to take this approach and get the sensors to really cover each other blind spots. So really, you're getting the disadvantages from all words in this approach. The second approach would be to fuse on a lower level. So imagine that I take the pixels from the camera and they give you a high resolution radar image in the form of pixels. It's not pixels, it's point cloud, we call it, because it's a different representation, but you can think of it as pixels. So you take pixels from the camera and pixels from the radar, and then fusing them together, then you can really compensate for each other disadvantages.
So you're mapping the radar input into a point cloud / pixels. So you're creating an image out of it, and then you're saying that you fuse those two.
On a pixel level. And this is a great advantage that you can really compensate from the disadvantage of each individual sensor. So you can use the camera to compensate for the radar disadvantages, and the radar to compensate for the camera disadvantages. And then really you get the benefits of the best performance out of the entire system. So it's a case of 1 + 1 = 3.
Let's talk about it a little bit. I mean, this is a very interesting concept. You're taking the radar signals and you're mapping it to, so to say, an image. Yeah. How do you do that? What is the mechanism?
So we even call it imaging radar because of that. It's only possible because of the high angular resolution. In essence, what you get in the end, you can think of the radar processing, the core radar processing, as just a high dimensional lens. So the signal processing chain of the radar signals, it is doing basically what the lens is doing for a camera.
You're receiving signals from the radar, right? Can you tell us, kind of like, and give a very, very dummy example, that how does the signal look like so that we can somehow get an idea how this mapping is done? What is the input? So what are you getting out of the radar?
Basically, you get waves. You get waves. You get, I would call it multi-dimensional waves. And basically what you're doing is a 4-dimensional FFT.
You're doing the 4-dimensional FFT in order to convert this into an image.
Yeah.
Okay. Before that, let's hold on to that for 1 second. You're getting waves, different waves. Let's say, we have this mug here, yeah, right? And your radar would sense this if we have relative velocity, if we're moving, and send me waves. Is it relative? I mean, tell me a little bit about the properties of the waves that you're receiving.
It really depends. Like, for example, your mug. So the radar would send waves probably from multiple sources. You have multiple antennas. So it transmits wave on the mug from different positions, right? And then you get spatial diversity. So it's like looking at the mug from different directions. And then you count the number of wavelengths between the radar and the mug. And this, in essence, is how you get the range. The actual technique is, you need to go deeper into the explanations. But in essence, in the end, what you're really doing is counting the number of wavelengths you get between the radar.
Got it. And the shape is different, and the number of wavelengths will be different since you're counting it in a different shape, right? And
right. But not all parts will reflect the energy back into the radar.
Yeah, that's the limitation of the radar. With a 4-dimensional Fourier transform, you convert it into a, like you said, a point cloud or a pixel, an array of pixel. I think that makes sense.
Another name for it, which might be even more accurate, is the occupancy grid.
Occupancy grid.
Occupancy grid, and kind of extract from that only the bins where you have energy, and this is what you really call radar point cloud.
I love it. Well, Noam, I can't help asking you, how does those images look if you look at it? Do they resemble reality, or, images coming out of wavelengths distribution? How do they look?
So I was telling people that I know how to look at 4-dimensional images now, after working with this technology for so long.
Yeah, 4-dimensional images. I'm coming to that. Tell me, how do they look first? Yeah.
Basically, when you project, so the 4 dimensions, you project them into 2 dimensions that you can see. When you project the image into range azimuth, which is really a simple way to display the radar image, you can really see it, and it's like looking on the world from the top, right? So let's say that you're driving in the street, and you have the camera perspective of looking forward. So when you project the radar image into a range azimuth dimension, you're really looking on the world from the top. So basically, you can see the shape of the street. You can see it's like playing a computer video game of watching the car from above and really controlling it. You can also project it in a different way on the azimuth elevation dimension, and then you can also put the radar point cloud on an image. If you project the radar information on azimuth elevation dimensions, you can project the radar on the camera image, and then you really see that you get reflections from the real targets, from cars, from pedestrians. You can actually understand which part of the object is projecting more or less. And then if you project it differently in range Doppler, azimuth Doppler, each kind of projection really gives you a different perspective of what you're seeing. So, for example, rotating an object like a fan or a car wheel or a drone rotor, if you look at it from range azimuth, elevation azimuth, doesn't matter. It looks like a point, basically. But if you look at it on the Doppler dimensions, then it's got a really unique pattern. So you start understanding a certain pattern goes with a specific object motion. You can identify pedestrian gates using the Doppler image, how the image looks like in the Doppler dimensions. There is a famous application in gesture recognition in the new Google Pixel phones. So they added gesture recognition with millimeter wave radar, with what I explained before, antenna on package approach. So you can understand like finger motions with the Doppler information. So really looking at the radar image and understanding all the details, you really have to think in a four-dimensional way.
That would have been my next question. I'm really fascinated. I'm literally getting goosebumps. What you're saying is, a really, really different way of looking at interpreting AI perception from the radar. I mean, what we have been actually focusing, which we did a great job. We have been doing image processing for the camera. We've been image processing and trying to understand what's going on. We actually have used radar for the distance, right? This was the primary use of the radar. Now, you are really coming up with stimulating me. This really excites me so much that you are taking radar to a whole new level. You're trying to extract images out of it, and you mentioned the word 4D images. Can you explain to our audience, what are 4D images? What are the dimensions we're talking about?
You get azimuth and elevation, like in the camera, and on top of it, you get range distance to the target, but it's an actual dimension. It's not a measurement. So imagine that you can take a cut in the image and look on all the targets in a specific range. They will be completely different from a different cut. So it's a full dimension orthogonal to the other dimensions. And Doppler is the same thing. Doppler is the fourth dimension, and it's the same thing. You can take a Doppler cut. So you can look in the image on all the stationary targets, for example. Let's say that you're stationary. You want to look on all the stationary targets, so it's Doppler zero cut. So you can just look on the image on the Doppler zero cut, and all the moving objects will not be there. It's a full dimension that you can look inside and holds a lot of information. One example of how Doppler information is very, very useful. So imagine that you have an object which is wide, like a car. It's big, it has a size, it's not a point target. Different points within this object have different Dopplers, depending on how it moves. So imagine that you're looking on a car from behind, and the car is trying to change lanes. If it's trying to change lanes to the left. So the left part is moving towards you, and the right part is moving away from you. So the radar is so sensitive that it can sense a small difference in these Dopplers from the two different parts of that same object, that really makes it the perfect sensor to have a intent estimation. You can have a real estimation, a good estimation of the intent of the car in front of you much earlier than any other sensors because of this Doppler information. So you're right, we've been using it to get range information, but the real treasure, the information that you have in the radar, is the Doppler information. It's very rich. You can get a lot of information from that dimension.
Love it, love it. So, I mean, the Doppler cut is really what's making it unique in a way. And we couldn't have done such things, such scenarios that you just mentioned. Well, we would have a different approach. From the camera perspective, yeah, the motion is changing. You can do some intent estimation, but now you can do fusion, right? You can fuse.
Do intent estimation from a single frame.
From a single frame, yeah.
You don't have to look between frames. A single frame tells you if the car is going to change lanes.
Yeah, because of the Doppler cut, Doppler resolution and Doppler cut. I love that. This is really interesting where we are at this point in the discussion. Now, I don't want to go to the cost part, the commercial part too early, because the technical discussion is way more exciting right now. So let's stay with this for another 5-10 minutes. You have this fancy information and you're doing the fusion. What is the hurdle? I mean, what if there is any disadvantage, anything that you think, you know, in terms of safety and all those in a radar, what would that be? What is the weakness of a radar? What is the blind? I mean, you mentioned the word blind spot. What would be the blind spot of a radar?
There are two blind spots or two main disadvantages of challenges, I would say. One of them is you really need to occupy quite a bit of bandwidth, and all radars work in the same band, in the same span, so you get interference.
Interference. Got it, yeah.
Radars interfering with one another is something we see in the field in test drives every day.
It happens in real life, yeah.
And it's causing a lot of problems, and coping with it is not as easy as it sounds. It's actually quite hard to cope with interferences. I would say that a lot of the techniques that was developed in the academic world, they have limitations. So the problem is really unsolved at the moment. So this is one challenge. The second challenge, I would say, is coping with multipaths, because for radar in this wavelengths, flat objects tends to behave like mirrors. So a radar in many ways, using a radar in a dense environment, in many ways, it's like driving in a field of mirrors, and you're trying to really understand which reflection is the real one. Those two are the most challenging points. The interference, I think, it's unsolved at the moment, but there are approaches that allow you to have its effects, the system performance, right? If you have interference, there is no way to really cope with it without affecting the radar performance at all. But you have all kinds of approaches for graceful degradation, which is good. So you're going to have performance degradation in a crowded scene, but it's not that bad. The multipaths problem, it's kind of more tricky, but with a good perception system, you can really track the objects and understand which one are the real ones and which ones are not the real ones. But I would say those are the two main disadvantages of the sensor.
Got it. So interference, as we know, this is a problem not only in radar technology, in many other technologies, and we don't really have a fancy way of solving this. This is a problem that has been unsolved, but a graceful degradation is, this would have been one of the safety questions that I would have had. Coming to the second, the flat objects for a radar. Can you explain that a little more? The scenario for where you have this issues.
Yeah. So imagine that you're driving on a highway and you have a guardrail, a flat guardrail between the two lanes. The radar energy is reflected right from it. So basically, and you got a car in the lane in front of you. So you see the reflections from the car in front of you, and you also see reflections coming from that guardrail that got like a two-way. It hit the guardrail, hit the target, hit the guardrail back, and got to the radar. And so it looks like a mirror. You see a reflection of the object from the other side of the guardrail. It's like looking in a mirror. It's the same thing. For radar, a lot of surfaces behaves like mirrors.
Okay, the guard lane will make me think that there is a car also on this side because of the reflection.
Yeah, exactly like a mirror. Yeah. So imagine that you're driving on a highway, and instead of a guardrail, you have a huge mirror for going to infinity. And you see the car in front of you, but you also see a car in the mirror.
Got that. And how do you deal with that problem again?
So you have to track both of them. So even if you're a human driver and you would have this kind of mirror, you would think that there's a car on the other lane. But those two cars move in the same way. You can compute correlation between the objects, right? And then these two objects are the same one because they always move in the same way.
I think here the fusion will also help you.
Exactly.
Yeah.
And the fusion tells you which one is the real one.
But in case of interference, I mean, graceful degradation right now, I think, is the only solution.
If you look at it from in different, I wouldn't say sensor, you got always in every car highlights and lowlights. This is the same interference. So you switch with the lowlights is a graceful degradation example.
Got it. So since we're talking about graceful degradation, this is a perfect segue to touch a little bit safety. You know, our podcast is called Autonomous Vehicle Safety and Security Podcast. So I can't help touching a little bit of safety scenarios because your product is safety relevant. Globally, we have, the industry has agreed on a standard, ISO 26262, and there has been an extension of safety of intended functionalities, SOTIF. How do you comply with these current standard in your manufacturing process and in your product?
So the ISO 26262 tells you that you have to think on all the internal faults that you might have in your system. We're doing all the hazard analysis, all the fault dependencies. We're doing all this rigorously, and we come up with safety mechanisms to detect those and alert on any safety events. We are also trying to be extra traditional in this sense that everything is a safety event, even if you have interference, which is a scenario where the radar is working well. There's no issue in the sensor, but still the radar performance is degraded. So we consider it as a safety event, and we notify on it. It might not be a destructive event, but the user or the car needs to know that the performance was degraded in such and such way. So everything that happens that we can detect, we alert on. And of course, we added all the extra mechanisms to make sure that everything is working, to evaluate the performance envelope in real time. This is part of the system design. So basically, we're aiming for ASIL B level as part of an ASIL D system, but on SOTIF is completely different question.
Totally. I agree. And it's a hard problem. SOTIF is a hard problem to solve. Let's stay with the ISO 26262 part. What you've said for another minute. It's a safety element out of context, right? Your radar. Yeah. Okay. Right. It's fantastic. Do you have some sort of certification for this safety element out of context in ASIL B qualification, as we call it? Is that qualified?
So we added all the internal mechanisms for our solution, and the goal is to get the certification in the middle of next year, and together with getting the product to a production level product.
Gotcha. Now let's talk about SOTIF. What's your take on SOTIF? You know, the main issue here is unknown, which may not be totally your concern within your territory because you're making the radar, not the whole system. What's your take on that?
Extremely difficult to really comply with that because it really asks you to assess scenarios and radar. Assessing scenarios for radar, it really depends on the texture of object in the scene, and a lot of things can happen. And to be honest, it's still for me looks almost impossible to map all the scenarios and what can happen in each scenario in a way which is meaningful. Which is the basis for the SOTIF, right? So you need to look on how the sensor will behave in each scenario. I think it could be very difficult task and will require not only like rigorous engineering, but also some sort of research. You really have to take into account a lot of physics in the structure of the objects. So a car with a certain shape and a car in a different shape will not necessarily behave the same way. Sometimes the car themselves are also reflecting other objects. You see, like, as I explained in Multipaths, like you have mirrors, so the cars themselves are causing multipaths. They are themselves the mirrors. So there's so many different complications that can happen in a sensor like radar or lidar or even camera, all sort of things that can happen. To be honest, I'm not sure I know how to comply with SODIF yet.
Nobody knows. Actually, you know, I mean, the thing is, when you know something, when there's something that you know, you can take safety measure. But we're talking about the unknown, the environment, the things that we don't know. And that is a problem even the safety ISO committee in safety could not solve. There is no solution for that. Now, we're heavily dependent on testings and stuff. And I agree with you, it is a difficult problem. Having said that, I want to touch on your commercial part a little bit. You said you're very, you know, in automotive industry, we all know that we talk about every sense in pieces. What's your monetization plan? I mean, you want to act as a tier 2 or tier 1 supplier. Where would you be in the automotive supply chain?
We are stationed as a tier 2. So what we sell is a chipset that enables this high performance. We sell this chipset to tier 1s, like traditional tier 1s, that provides the radar module. It's a tier 2 business model. It includes transmitter chip, has a lot of transmitter channel, and the receiver chip have a lot of receive channels. The third component is the processor, which we have embedded in the processor our secret sauce or the signal processing algorithms that is necessary in order to process in real time all this huge amount of information. One of the problems that you get when you're dealing with 4-dimensional images is now that the image size becomes huge. So we didn't discuss that, but just imagine that you have a camera image that takes, I don't know, 10 megabytes, 20 megabytes. This is a 2-dimensional image. So a radar image, because it's 4-dimensional, can take 100 gigabits of information. So processing it and handling it up to the point cloud level. The point cloud might be small, but the radar image before the point cloud is huge. So this really requires dedicated hardware and dedicated algorithms embedded in that hardware. And this is the third chip, the processor chip. This is what is doing.
Got it. I think you've already answered my next question. You know, I was going to ask you, where do you do the computation that fast? Because automotive industry is, you know, we're talking about not milliseconds, sometimes even in microseconds of performance. I love that. Noam, I think this conversation was really, really exciting. Thank you so much for being with us and taking all these questions. It was really exciting.
Thank you.
So thank you so much for watching. It was Noam Arkind from Arbe who talked about all these exciting stuff about radar technology. If you have questions, comments, please write in the comment section below. Please smash the thumbs up button if you have liked this video, and subscribe to our channel, and also share this video with your peers. So thank you so much again for watching.